Radioisotope thermoelectric generator. A radioisotope thermoelectric generator is a type of nuclear battery that uses an array of thermocouples to convert heat from the decay of a suitable radioactive material into electricity by the Seebeck effect. The design of an RTG is simple by the standards of nuclear technology. The main component is a sturdy container of a radioactive material, the fuel. Thermocouples are placed in the walls of the container, with the outer end of each thermocouple connected to a heat sink. Typically, a large number of thermocouples are connected in series to generate a higher voltage. A thermocouple is a sensor that measures temperature. It consists of two different types of metals joined together at one end. When the junction of the two metals are heated or cooled, there is a continuous current which flows in the thermoelectric circuit. The voltage created can be correlated back to the temperature. The Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. The RTG was invented in 1954 by Mound Laboratories in Miamisburg, Ohio by Ken Jordan and John Burden. The project was led by Dr. Bertman C. Blank. Jordan and Burden worked on an Army Signal Corps contract beginning on the 1st of January 1957 to conduct research on radioactive material and thermocouples suitable for direct conversion of heat to electrical energy using polonium-210 as the heat source. Polonium-210 is an isotope of polonium. It undergoes alpha decay to stable 206 lead, with a half-life of 138.376 days, the longest half-life of all naturally occurring polonium isotopes. This type of generator has no moving parts. There is no risk of parts wearing out or malfunctioning, which is ideal for remote and harsh environments for extended periods of time. The expense of RTGs tends to limit their use to niche applications in rare or special situations. Radioisotope thermoelectric generators have been used as power sources in satellites, space probes, and uncrewed remote facilities, such as a series of lighthouses built by the Soviet Union inside the Arctic Circle. The first RTG launched into space by the United States was SNAP-3B for navigational satellites in 1961, powered by 96 grams of plutonium-238 metal, and was launched aboard the Navy Transit for a spacecraft. One of the first terrestrial uses of RTGs was in 1966 by the U.S. Navy at uninhabited Fairway Rock in Alaska. There were at least 6 units deployed. Known as SNAP 7A, D, and F, they were designed for marine applications such as lighthouses and buoys. They produced 30 watts of electricity and used about 4 kilograms of strontium-90. They were very large units weighing between 1,870 and 6,000 pounds. RTGs were used at that site until 1995. Strontium-90 is a radioactive isotope of strontium produced by nuclear fission, with a half-life of 28.8 years. It undergoes beta decay into yttrium-90 with a decay energy of 0.546 mega-electron volts. The radioactive decay of strontium-90 generates a significant amount of heat, 0.95 in the form of pure strontium metal, or about 0.46 as strontium titanate, and is cheaper than plutonium-238. Strontium-90 can also find uses in industry for thickness gauges, in medicine for superficial radiotherapy of some cancers, and in aerospace as blade inspection method in some helicopters. In the past, small plutonium cells were used in implanted heart pacemakers to ensure a very long battery life. As of 2004, about 90 were still in use. By the end of 2007, the number was reported to be down to just 9. The Mound Laboratory Cardiac Pacemaker Program began on 1st of June 1966 in conjunction with NUMEC, the Nuclear Material and Equipment Company. When it was recognized that the heat source would not remain intact during cremation, the program was canceled in 1972 because there was no way to completely ensure that the units would not be cremated with their user's body.